Welcome to today's problem walkthrough. In this session, we'll be diving into LeetCode problem number 975, titled Odd Even Jump. This is a fascinating problem that challenges us to work with arrays and dynamic programming to determine how many starting indices lead to a successful sequence of odd and even jumps. Let's get started and break it down step by step. In this problem, we are working with an integer array called ARR, where the indices start at 0. The goal is to determine how many starting indices in the array are considered good. A starting index is good if you can jump from that index, following specific rules, and eventually reach the last element of the array. The jumping rules depend on whether the jump is an odd jump or an even jump. For an odd jump, you can move to the smallest index j such that the value at ARR j is greater than or equal to the value at ARR I. For an even jump, you move to the smallest index j such that the value at ARR j is less than or equal to the value at ARR I. Importantly, the first jump will always start as an odd jump. The output of the problem is the total number of indices from which you can reach the end of the array using these rules. Let's go through an example to make this clearer. Consider the input array ARR equals 10, 13, 12, 14, 15. The output here is 2, meaning there are 2 starting indices that are good. For instance, starting from index 1, where the value is 13, the first jump is an odd jump. Here, we look for the smallest index j such that ARR j is greater than or equal to 13. This takes us to index 2, where the value is 14. For the next jump, which is now an even jump, we look for the smallest index j such that ARR j is less than or equal to 14. This takes us to index 4, where the value is 15. Since we've reached the last index, index 1 is considered good. Now, let's analyze another starting index in the same example. Starting from index 3, where the value is 14, the first jump is an odd jump. Following the rule, we look for the smallest index j such that ARR j is greater than or equal to 14. This leads us to index 4, where the value is 15. Since we've now reached the last index, index 3 is also considered good. However, for all other starting indices in this array, it is not possible to reach the last index by following the jumping rules. This is why the output for this example is 2. Let's look at another example. For the input ARR equals 2, 3, 1, 1, 4, the output is 3, as there are 3 good starting indices. Starting from index 0, with the value 2, the first jump is an odd jump. The smallest index j such that ARR j is greater than or equal to 2 is index 1, where the value is 3. For the next jump, now an even jump, the smallest index j such that ARR j is less than or equal to 3 is index 4, where the value is 4. From here, we've reached the last index, so index 0 is good. Similarly, starting from index 1, the odd jump directly takes us to index 4, which is the last index. Starting from index 4 itself, we are already at the last index, so it is also good. No other starting indices allow us to reach the end. Here's another example with the array ARR equals 5, 1, 3, 4, 2. The output is 3, as there are 3 starting indices that are good. Let's break this down. Starting from index 2, where the value is 3, the first jump is an odd jump. The smallest index j such that ARR j is greater than or equal to 3 is index 3, where the value is 4. The next jump, an even jump, takes us to index 4, where the value is 2. Since we've reached the last index, index 2 is good. Similarly, starting from index 3, an odd jump takes us directly to index 4, so index 3 is also good. Starting from index 4, we are already at the last index, making it good as well. No other indices allow for a valid path to the end. When solving this problem, it's helpful to consider specific edge cases and patterns. For instance, if the array has only one element, the answer is always 1 because the single element is already at the end. Arrays with strictly increasing or strictly decreasing values may present simpler jumping patterns, as the jumps will always progress in a predictable manner. On the other hand, arrays with repeated values require careful handling to resolve ties. For example, when multiple indices qualify for the smallest or largest valid j during odd or even jumps, you must ensure that you select the smallest possible index. Developing an efficient approach to handle these scenarios is key to solving the problem within the constraints. To solve this problem, we need to determine how many starting indices in the array allow us to reach the end using a specific set of rules for jumping. The rules differ depending on whether the jump is odd or even. For an odd jump, we move to the smallest index greater than the current index where the value is at least as large as the current value. For an even jump, we move to the smallest index greater than the current index where the value is at most the current value. The challenge lies in efficiently calculating these jumps for each index in the array. Key insights include recognizing that both jump types rely on sorting or ordering, which suggests the use of data structures optimized for such operations. Additionally, the problem can be broken into subproblems by determining for each index whether it can eventually reach the end using odd and even jumps recursively. However, a naive approach that checks all possible jumps for each index would be computationally expensive, requiring n² time. Instead, we can leverage optimized techniques like monotonic stacks or binary search trees to reduce the complexity of finding the next valid index, bringing the solution closer to n log n. Several approaches were considered to solve this problem. The first is a brute force method, where for each index, we simulate all possible paths using odd and even jumps to determine if they lead to the end. While this approach is straightforward conceptually, it is computationally expensive, as it involves nested iterations over indices and jumps, resulting in a time complexity of n². For larger inputs, such as n equals 10,000, this method becomes impractical. The second approach is an optimized one that combines dynamic programming with monotonic stacks. Here, we pre-compute the next valid index for both odd and even jumps more efficiently. The steps include sorting the indices based on the array values in ascending order for odd jumps and descending order for even jumps. We then use monotonic stacks to calculate the next valid index for each jump type. Using this pre-computed information, we populate two dynamic programming arrays, one that tracks whether an index can reach the end with an odd jump and another that does so for even jumps. By iterating backward through the array, we ensure that results are reused, avoiding redundant calculations. This approach has a time complexity of n log n, dominated by the sorting step, and is much more scalable for large inputs. The chosen strategy for solving this problem is the optimized approach that combines dynamic programming with monotonic stacks. This method strikes a balance between efficiency and clarity, making it both effective and relatively simple to implement. Sorting the indices and using monotonic stacks to pre-compute the next valid indices ensures that we minimize redundant computations. By storing results in dynamic programming arrays, we avoid recalculating whether an index can reach the end, which significantly reduces the overall complexity. When comparing approaches, the brute force method, though conceptually simple, is impractical for larger inputs due to its quadratic runtime. On the other hand, the optimized approach, with its n log n complexity, scales well for input sizes up to the problem's constraints. We also considered alternatives like binary search trees for finding the next valid index, which would also achieve logarithmic time complexity for successor searches. However, monotonic stacks are both simpler to implement and free of the overhead associated with maintaining a balanced tree structure. In conclusion, the optimized approach using dynamic programming and monotonic stacks is the most suitable solution, leveraging sorting and successor search to deliver an efficient and easy-to-understand implementation. In this problem, our goal is to determine how many starting indices in the array allow us to reach the last index by following a sequence of odd and even jumps. The key lies in understanding how these jumps are defined. For an odd jump, we move from index I to the smallest index j greater than I where the value at j is at least as large as the value at I. If no such index exists, the jump is invalid. For an even jump, we move to the largest index j greater than I where the value at j is at most the value at I. Again, if no valid index exists, the jump fails. The objective is to count how many starting indices can successfully navigate to the last index using a valid sequence of these odd and even jumps. Understanding these rules is the foundation of our approach to solving the problem effectively. To solve this problem, we start by initializing some key data structures. We create two Boolean arrays, odd_reachable and even_reachable, both of size n, where n is the length of the input array. These arrays will help us track whether it's possible to reach the last index starting from each index using odd or even jumps, respectively. By definition, the last index is always reachable from itself, so we initialize the last entries of both arrays to true. Next, we need to determine the next valid indices for each odd and even jump. To do this efficiently, we use a monotonic stack. For odd jumps, we sort the indices of the array by their values in ascending order, and in the case of ties, by their indices in ascending order. The stack helps us compute the smallest valid j for each I. For even jumps, we sort the indices by their values in descending order, again breaking ties by indices, and use the stack to find the largest valid j for each I. The results are stored in the next_odd and next_even arrays, which map each index to its corresponding valid jump destination. With the next indices determined, we move on to the dynamic programming step. Here, we traverse the array in reverse, starting from the second to last index and moving to the first, to fill the odd_reachable and even_reachable arrays. For each index I, we check the next jump destinations. If next_odd, I, is not -1, it means there's a valid odd jump, and we set odd_reachable, I, to match the value of even_reachable at the destination index. Similarly, if next_even, I, is not -1, we set even_reachable, I, to match the value of odd_reachable at its destination. This way, we propagate the reachability status backward through the array using the pre-computed next indices. After completing the traversal, we count how many indices in the odd_reachable array are marked as true, since these are the starting indices that can successfully reach the last index. This systematic approach ensures we evaluate the problem efficiently without redundant calculations. Several data structures are at the heart of this solution. The odd_reachable and even_reachable Boolean arrays track whether the last index is reachable from each index via odd or even jumps. The next_odd and next_even arrays store the valid next indices for odd and even jumps, respectively. The monotonic stack is crucial for efficiently computing these next indices based on sorted order, avoiding the inefficiency of a brute force search. When handling edge cases, we must account for scenarios like single-element arrays, where all indices are trivially reachable, or arrays with duplicate values, where the sorting logic ensures ties are resolved correctly. Additionally, for arrays with decreasing values, the solution must handle cases where no valid jumps exist by marking the corresponding entries in the next index arrays as -1. In terms of complexity, sorting the indices takes O(n) log n, while the monotonic stack operations in dynamic programming traversal are O(n), resulting in a total time complexity of O(n) log n. The space complexity is O(n), due to the additional arrays we maintain for the solution. This combination of efficient data structures and algorithms makes the approach scalable even for large input sizes. In this implementation, we start by importing the sorted_dict class from the sorted_containers module, which will help us efficiently maintain a sorted map while iterating through the array. Inside that odd-even jumps function, the first thing we do is initialize some variables. We get the length of the input array ARR and handle the edge case where the array has only one element, in which case the result is simply 1 since there are no jumps needed. Next, we define two lists, odd_next and even_next, both initialized with -1 for all positions. These lists will store the indices of the next positions we can jump to, depending on whether the jump is odd or even. Then, we create a sorted_dict called sorted_map to help calculate these next jumps efficiently. We iterate through the array backward, starting from the last element. For each index, we extract the current value val. To determine the next index for an odd jump, we first check if val is already present in sorted_map. If it is, we simply look up its corresponding index. If it isn't, we use the bisect_left method to find the smallest key in sorted_map that is greater than or equal to val. If such a key exists, we retrieve its corresponding index and store it in odd_next. Similarly, for even jumps, we use the bisect_right method to find the largest key in sorted_map that is less than or equal to val. The calculated index for the even jump will be stored in the even_next list. If the calculated index for the even jump is valid, meaning it's greater than or equal to 0, we store it in the even_next list at the current position. After determining the next indices for both odd and even jumps, we update the sorted_map to include the current value val and its index I. This ensures that the sorted map remains accurate for subsequent calculations as we continue iterating backward through the array. Once we've built the odd_next and even_next lists, we initialize two dynamic programming arrays, odd_reachable and even_reachable, both filled with false. These arrays will help us track whether we can reach the end of the array starting from each index, depending on whether the first jump is odd or even. The last index is always reachable, so we mark it as true for both arrays. Next, we iterate backward through the array again, starting from the second to last index. For each index, we check if there's a valid next index for an odd jump. If there is, we update odd_reachable for the current index based on the value of even_reachable at the next index. Similarly, if there's a valid next index for an even jump, we update even_reachable for the current index based on the value of odd_reachable at the next index. Finally, we count and return the number of indices where the first jump is an odd jump, which corresponds to the sum of true values in the odd_reachable array. Here, we start by importing the necessary libraries and defining the solution class. The main focus is the odd-even_jumps method, which takes an integer array as input. First, we calculate the length of the array and handle the base case where the array contains only one element. In such a case, the result is simply 1 since you are already at the end of the array. Next, we initialize two arrays, odd_next and even_next, to store the indices of the next valid jumps for odd and even numbered jumps respectively. Both are initially filled with -1 to indicate that no jump is possible by default. We also initialize a tree map, which will help us efficiently find the smallest greater or largest smaller keys for the odd and even jumps. Then, we loop through the array in reverse order, starting from the last index. Within this loop, we first determine the next index for an odd jump. If the current value already exists as a key in the tree map, we set the corresponding odd next index to the stored value. Otherwise, we use the ceiling entry method to find the smallest key greater than or equal to the current value, and if such a key exists, we update the odd next array accordingly. Now, we focus on finding the next index for an even jump. Using the floor entry method, we locate the largest key smaller than or equal to the current value in the tree map. If such a key exists, we update the even next array at the current index. After determining the next indices for both odd and even jumps, we update the tree map by inserting the current value with its index. This ensures that the map reflects the latest state for subsequent iterations. Next, we define two Boolean arrays, odd-reachable and even-reachable, to track whether the end of the array is reachable starting from each index, using odd or even jumps respectively. We initialize the last index of both arrays to true since the end is trivially reachable from itself. Then, working backward through the array, we use the odd next and even next values to update the reachability arrays. Specifically, an index is marked as reachable via an odd jump if the corresponding even reachable index it points to is true, and vice versa for even jumps. This step ensures that we propagate the reachability information backward through the array. Finally, we calculate the result by iterating through the odd reachable array and counting the indices where the value is true. These represent the starting indices from which the end of the array can be reached using a sequence of odd and even jumps. Once the count is complete, we return the result, which is the total number of such starting indices. This concludes our implementation of the odd-even jumps method, providing an efficient solution to determine the number of valid starting points in the array. Here, we start with the example input array ARR equals 10, 13, 12, 14, 15. The first step is to initialize our variables. We set n to the length of the array, which is 5. Next, we initialize two arrays, odd_next and even_next, both filled with -1, to eventually store the indices of odd and even jump targets for each index. We also create an empty sorted dict called sorted_map to maintain indices of the elements in sorted order as we process the array. Now, we calculate the odd_next and even_next arrays by iterating through the input array from the last index to the first. At index 4, the value is 15. Since sorted_map is initially empty, there are no valid targets for odd or even jumps. We then update sorted_map to include the value 15 at index 4. At index 3, the value is 14. For an odd jump, we look for the smallest value greater than or equal to 14 in sorted_map, which is 15. The corresponding index is 4, so we set odd_next 3 equals 4. For an even jump, we try to find the largest value smaller than 14, but there are no such values, so even_next 3 remains -1. Finally, we update sorted_map to include the value 14 at index 3, resulting in 14, 3, 15, 4. At index 2, the value is 12. For an odd jump, the smallest value greater than or equal to 12 in sorted_map is 14, which corresponds to index 3. Thus, odd_next 2 equals 3. For an even jump, there's no smaller value than 12, so even_next 2 equals -1. We then update sorted_map to include the value 12 at index 2, making it 12, 2, 14, 3, 15, 4. At index 1, the value is 13. For an odd jump, the smallest value greater than or equal to 13 is 14, which leads to index 3, so odd_next 1 equals 3. For an even jump, the largest value smaller than 13 is 12, which corresponds to index 2. Thus, even_next 1 equals 2. Updating sorted_map to include 13, we now have 12, 2, 13, 1, 14, 3, 15, 4. Finally, at index 0, the value is 10. The smallest value greater than or equal to 10 is 12, corresponding to index 2, so odd_next 0 equals 2. For an even jump, there's no smaller value than 10, so even_next 0 remains -1. After updating sorted_map with 10, it becomes 10 o'clock, 12, 2, 13, 1, 14, 3, 15, 4. With the odd_next and even_next arrays calculated, the next step is to initialize two Boolean arrays, odd_reachable and even_reachable, to track whether each index can be reached by odd or even jumps. Both arrays are set to all false initially, except for the last index, which is set to true because it is trivially reachable. Now, we process the indices in reverse to determine reachability. At index 3, odd_next 3 is 4, and since even_reachable 4 is true, we set odd_reachable 3 to true. For even jumps, even_next 3 is -1, so even_reachable 3 remains false. At index 2, odd_next 2 is 3, but even_reachable 3 is false, so odd_reachable 2 remains false. Similarly, even_next 2 is -1, so even_reachable 2 is also false. At index 1, odd_next 1 is 3, and since even_reachable 3 is true, we set odd_reachable 1 to true. For even jumps, even_next 1 is 2, but odd_reachable 2 is false, so even_reachable 1 remains false. At index 0, odd_next 0 is 2, but even_reachable 2 is false, so odd_reachable 0 remains false. For even jumps, even_next 0 is -1, so even_reachable 0 remains false. After processing all indices, the odd_reachable array is false, true, true. This means that indices 1, 3, and 4 are reachable via odd jumps. Summing up the true values in odd_reachable, we find that the total number of reachable indices is 3. Now, let's look at another example with the input array ARR equals 5, 1, 3, 4, 2. First, we initialize the variables. The length of the array, n, is 5. Both odd_next and even_next arrays are initialized to -1, -1, -1, -1, -1, and sorted_map is an empty sorted dict. While calculating jumps, at index 4 with value 2, no jumps are possible since sorted_map is empty. We update sorted_map to 2, 4. At index 3 with value 4, the smallest value greater than or equal to 4 is 4, leading to index 4, so odd_next 3 equals 4. We update sorted_map to 2, 4, 4, 3. At index 2 with value 3, the smallest value greater than or equal to 3 is 4, leading to index 3, so odd_next 2 equals 3. Updating sorted_map gives 2, 4, 3, 2, 4, 3. At index 1 with value 1, the smallest value greater than or equal to 1 is 2, leading to index 4, so odd_next 1 equals 4. After updating sorted underscore map, it becomes 1, 1, 2, 4, 3, 2, 4, 3. At index 0 with value 5, no valid jumps are possible, and we update sorted underscore map to 1, 1, 2, 4, 3, 2, 4, 3, 5 o'clock. Finally, for reachability, the odd_reachable array is false, true, 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 meaning indices 1, 2, 3, and 4 are reachable via odd jumps. The total number of reachable indices is 4. For the two examples, the final outputs are 3 and 4, respectively. To analyze the time complexity of the optimized solution for odd-even jump, we start by examining how the odd_next and even_next arrays are constructed. This process involves iterating through the array ARR in reverse, from the last index to the first. At each step, operations are performed using a sorted dict, which is a data structure that maintains the keys in sorted order. Key operations include bisect_left to find the smallest key greater than or equal to the current value, and bisect_right to find the largest key less than or equal to the current value. Both of these operations use binary search and therefore take log n time. Additionally, fetching a key value pair with peak item is O(1), and inserting a new key value pair into the sorted dict takes log n. Because these operations are repeated for each element in the array, and there are n elements total, the overall time complexity of building these arrays is n*log n. This step dominates the computational cost of the algorithm. Once the odd_next and even_next arrays are constructed, the algorithm proceeds with a dynamic programming traversal to determine reachability for each index. This involves simple lookups and assignments within the odd_next and even_next arrays. Since these operations take constant time, or O(1), for each index, and there are n indices in total, this step contributes n time complexity. When combining this with the earlier step of building the sorted dict, the n*log n term dominates the total time complexity, making the overall time complexity of the optimized solution n*log n. The contribution from the dynamic programming step is negligible in comparison to the sorting and binary search operations. Now let's consider the space complexity of the algorithm. First, the sorted dict data structure is used to store distinct elements of ARR as keys, with their indices as values. In the worst case, where all elements in ARR are unique, the sorted dict will store n key value pairs, resulting in n space usage. Next, the odd_next and even_next arrays are each of size n, and together they also require n space. Additionally, the DP arrays odd_reachable and even_reachable are Boolean arrays of size n, used to track reachability status for each index. These arrays also require n space in total. Thus, these primary components contribute n space usage collectively. Aside from the primary data structures, there are a few auxiliary variables used throughout the algorithm, such as val, higher, and lower. These variables require a constant amount of space, or O(1), as their usage does not scale with the size of the input array. Combining all these factors, the space complexity of the algorithm is dominated by the sorted dict, odd_next, even_next, and DP arrays, each of which scales linearly with the size of the array. As a result, the overall space complexity of the algorithm is n. To put this into perspective, let's compare the optimized solution to a brute force approach. In a brute force solution, you would need to explore all possible jump sequences for each starting index to determine if the end of the array is reachable. This approach would involve exponential growth in the number of possible paths due to branching, leading to a time complexity of n*2 to the power of n. The space complexity for the brute force method would still be n, to account for the recursion stack or memoization. In contrast, the optimized solution uses a sorted dict for efficient computation of the next indices for odd and even jumps, and dynamic programming to track reachability. This reduces the time complexity from exponential to n*log n, making it far more practical for large input sizes, while maintaining the same n space complexity. Finally, let's discuss the best, average, and worst case scenarios for this algorithm. In the best case, where all elements in ARR are identical, the operations on the sorted dict are minimal, but the time complexity remains O n asterisk log n due to the inherent sorting operations. In the worst case, where all elements in ARR are distinct, each index requires full binary search updates in the sorted dict. This scenario also results in O n asterisk log n time complexity, which is the dominant case and matches the overall complexity of the algorithm. Mathematically, the O n asterisk log n time complexity arises because each of the n iterations involves binary search and insertion operations, both of which are logarithmic. The O n space complexity is similarly straightforward, as it comes from the linear storage requirements of the arrays and dictionary. This balanced and optimized design makes the solution both efficient and scalable for a wide range of inputs. When tackling the odd-even jump problem, there are a few common mistakes that can trip up even experienced coders. First, it's crucial not to confuse the rules for odd and even jumps. Remember, an odd jump seeks the smallest number greater than or equal to the current value, while an even jump targets the largest number less than or equal to the current value. Mixing these up can lead to incorrect results, so consider using helper functions or clear comments to keep the logic separate and easy to understand. Another frequent issue is relying on an inefficient brute force implementation. Simulating every possible jump for each starting index creates a time complexity of O n squared, or worse, which becomes impractical for large input sizes. Instead, optimize your approach by pre-computing the next valid jump indices using data structures like sorted maps or monotonic stacks. Finally, be mindful of how duplicate values are handled in the array. If multiple indices share the same value, the smallest index rule for odd jumps is often overlooked, leading to errors. To address this, ensure that your implementation resolves ties correctly, prioritizing the smallest index when determining the next jump. Now, it's important to consider edge cases that could cause unexpected behavior. For instance, single-element arrays or arrays where all values are identical might behave differently from typical cases. Testing with edge cases such as 1, 5, 5, 5, or 2, 1 can help ensure your logic is robust. Another common pitfall is overcomplicating space usage. Storing excessive intermediate data, like all possible paths for jumps, can lead to memory inefficiencies. Instead, streamline your solution by focusing only on the essential data, such as the next jump indices for odd and even jumps. By keeping your implementation lean and testing thoroughly, you can avoid these issues and create a more efficient and reliable solution. Understanding the deeper insights behind this problem can help you master it and explain your solution effectively during interviews. At its core, the odd-even jump problem combines dynamic programming with monotonic stacks or sorted maps to pre-compute the next valid jump indices efficiently. A key pattern to recognize is that this problem can be viewed as a graph traversal, where valid jumps define the graph edges. Dynamic programming then allows you to propagate reachability information efficiently across the graph. To optimize your solution, focus on reducing the time complexity by using data structures like sorted dict in Python or tree map in Java. These allow you to pre-compute the next jump indices in O n log n time, which is a significant improvement over brute force approaches. When explaining this problem, break your process into clear steps. First, calculate the next valid index for both odd and even jumps. Second, use backward dynamic programming to determine which indices can reach the end. And finally, count the starting indices that meet the condition. This structured approach not only solves the problem efficiently but also demonstrates a clear thought process. The techniques used in this problem are applicable to several related problems, making it a valuable learning opportunity. For example, LeetCode 42, Trapping Rainwater, also leverages the concept of monotonic stacks, while LeetCode 352, Data Stream as Disjoint Intervals, involves the use of sorted maps. Another related problem is LeetCode 456, the 132 pattern, which utilizes stacks to find the next greater element. Exploring these problems can deepen your understanding of the underlying patterns and techniques. Additionally, while the brute force approach to odd-even jump is simple to implement, it's highly inefficient, often resulting in O n squared or worse. A more practical alternative is using a monotonic stack to efficiently calculate the next greater or lesser index for odd and even jumps. This reduces the time complexity to O n log n, while providing a solid foundation for understanding stack-based algorithms. Another highly efficient approach is to use sorted maps, such as sorted dict in Python, to determine the smallest or largest valid index for odd and even jumps. This method is intuitive for those familiar with sorted data structures and offers a clean and efficient way to pre-compute the necessary indices. For Java programmers, the tree-set data structure serves a similar purpose, allowing you to find the next values for jumps efficiently. While both approaches achieve the same complexity, they cater to different programming environments and skill sets. By mastering these techniques and understanding their trade-offs, you'll be well equipped to solve this problem and others like it. Great job! Today, we explored the odd-even jump problem and applied dynamic programming alongside monotonic stacks to arrive at an efficient solution. Remember, mastering the concepts we covered today will help you tackle a variety of challenging problems in competitive programming and technical interviews. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!